Gravity is pulling you down right now. You can feel it. You are sitting in that chair, and the earth, this enormous ball of rock and iron, seems to be reaching up through the floor and dragging you toward its center. Every second of every day, gravity grabs you. It grabs the coffee in your mug. It pulls the rain from the sky. It keeps your feet pressed against the ground. You learned this before you even knew the word gravity, the first time you fell and hit the floor. Down was not a theory. It was an experience. Everything in your daily life confirms it. You drop a ball and it falls. You jump and you come back down. You throw something sideways and it curves toward the earth. The story feels complete. A force reaches out across space and pulls everything inward. And that story is wrong. Not slightly wrong, not technically incomplete, but wrong at its core. It works beautifully. It predicts the motion of planets. It sent astronauts to the moon. It calculates trajectories with stunning precision, but it does not describe what is actually happening. What is actually happening is stranger than common sense allows. And once you see it clearly, the simple act of sitting in a chair will never feel the same again. In the late 17th century, Isaac Newton did something so powerful that it reshaped humanity's understanding of the universe. He realized that the force causing an apple to fall from a tree was the very same force keeping the moon in orbit around the earth. That insight collapsed the wall between heaven and earth. Before Newton, the skies and the ground were governed by different rules in the human imagination. The planets moved in a divine realm, and falling stones belonged to a separate world. Newton unified them with a single law. Every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. Double the mass, and the force doubles. Double the distance, and the force becomes 1/4 as strong. One clean equation, simple enough to write on a page, yet powerful enough to map the cosmos. And it worked. It worked with an authority that demanded trust. Using Newton's law, Edmund Halley predicted that a comet observed in 1682 would return decades later. He did not live to see it. But in 1758, the comet appeared almost exactly on schedule, confirming the calculation of a dead man. Astronomers later noticed that Uranus did not follow the precise path Newton's law predicted. Instead of abandoning the theory, they assumed another unseen planet must be tugging on it. Two mathematicians independently calculated where that planet should be. Telescopes were aimed at that exact patch of sky, and Neptune was found almost precisely where the mathematics said it would be. A planet discovered not by looking first, but by trusting an equation. That kind of success builds conviction. It convinces generations that they are holding truth itself. Newton's gravity explained the tides as the pull of the moon on Earth's oceans, stronger on the near side and weaker on the far side, creating two bulges of water that sweep around the globe. It explained why Earth is not a perfect sphere but slightly flattened at the poles and wider at the equator, because rotation flings matter outward while gravity pulls inward, and the planet settles into a balance between the two. It explained the arcs of cannonballs, the paths of projectiles, the motion of satellites, and the stability of planetary orbits. With Newton's law, engineers could calculate trajectories, sailors could refine navigation, and astronomers could chart the future positions of worlds centuries in advance. Gravity became a universal pulling force, invisible yet measurable, reaching across empty space and binding the universe together. The picture it painted was clear and intuitive. The Earth has mass. You have mass. The Earth's mass generates a gravitational force that reaches outward and pulls you toward its center. When you stand on the ground, the surface pushes back and prevents you from falling through. But the pull remains constant, pressing you downward. That pressing sensation is your weight. The heavier you are, the stronger the pull. The explanation aligns perfectly with experience. You release an object and it accelerates toward the ground. You toss something upward and it slows, stops, and falls back. You watch the moon circle the earth and imagine an invisible tether keeping it bound. Everything about daily life reinforces the same conclusion. There is a force. It points down. Case closed. For more than 2 centuries, this framework dominated physics not because it was convenient, but because it was extraordinarily successful. It predicted, explained, and unified. It turned the heavens into a system governed by the same mathematics as a falling stone. It gave humanity confidence that the universe was comprehensible, orderly, and governed by precise laws. When something deviated, scientists searched for hidden masses, unseen influences, subtle corrections, but they rarely doubted the foundation itself. Newton's gravity was not merely a theory. It was the architecture of reality as understood by the modern mind. It felt solid. It felt complete. And precisely because it felt so complete, it took an even more radical idea to reveal that beneath its elegance there was a deeper truth waiting to overturn the very meaning of what it means to fall. For all its brilliance, Newton's picture carried 2 cracks from the very beginning. Cracks so subtle that they were hidden beneath centuries of success. The first crack was action at a distance. In Newton's law, gravity acts instantaneously across any separation. The sun pulls on the earth right now across 93 million miles of space with no delay. If the sun were to vanish this instant, Newton's equations say, the earth would immediately leave its orbit and fly off in a straight line. Not 8 minutes later when the last sunlight fades, but immediately, faster than light. Newton himself was deeply uncomfortable with this. He wrote that the idea of one body acting upon another through empty space without anything mediating the action was so absurd that no competent thinker should accept it. Yet he had no mechanism to offer. He provided the mathematics and refused to speculate about how the force was transmitted. For more than 200 years, physics tolerated this silent mystery because the numbers worked. Planets moved as predicted. Tides rose and fell on schedule. Cannons and comets obeyed the same equation. The success was so overwhelming that the absence of a mechanism was quietly ignored. But the crack never disappeared. A force reaching across a vacuum without a messenger is not an explanation. It is a placeholder. The second crack was even stranger because it did not look like a flaw at first. It looked like a coincidence so perfect that people stopped noticing it. According to Newton, the gravitational force on an object is proportional to its mass. The more mass, the stronger the pull. But the resistance of an object to acceleration, its inertia, is also proportional to its mass. When you write the equations of motion, the mass in the force term cancels the mass in the inertia term. The result is that every object accelerates at the same rate in a gravitational field, regardless of its mass or composition. A hammer and a feather in a vacuum fall side by side. Galileo suspected this long before Newton by rolling balls down inclined planes. Centuries later, astronauts on the moon dropped a hammer and a feather and watched them strike the lunar surface together. The equality holds to extraordinary precision for every material ever tested. In Newton's framework, this equality has no deeper explanation. Gravitational mass, which determines how strongly gravity pulls, just happens to be numerically equal to inertial mass, which determines how hard it is to accelerate something. They are conceptually different quantities, yet they are always equal, not approximately equal, not statistically close, but equal to astonishing accuracy. For any other force, this would not occur. If you double the electric charge on a particle, you double the electric force on it. But you do not double its inertia. Electric acceleration depends on charge to mass ratio. Gravity alone produces acceleration independent of composition. That is not how forces normally behave. It is as if nature is whispering that gravity is not truly a force in the same category as electricity or magnetism. These two cracks point in the same direction. Action at a distance suggests something incomplete about the mechanism. The equality of gravitational and inertial mass suggests something incomplete about the nature of the interaction itself. Together they undermine the simplicity of the picture. If gravity were a standard force, one should be able to describe how it propagates and why it couples identically to every form of matter. Newton's equations give no such explanation. They provide predictive power, but not conceptual closure. For centuries, physics moved forward with this elegant but unfinished framework, unaware that these cracks were not minor imperfections, but clues that gravity might not be a pulling force at all, but something far more radical hiding beneath the surface of common sense. Now imagine a simple experiment. You are inside a sealed box with no windows, no view of the outside world, completely cut off from any reference point. You are standing on the floor and you feel your normal weight pressing your feet downward. You drop a ball and it falls to the floor. Everything behaves exactly as it does on the surface of the earth. The question is simple. Are you on earth? The obvious answer is yes. But there is another possibility. You could be far out in deep space, nowhere near any planet or star, inside a rocket that is accelerating upward at 8 meters per second squared. The engine beneath you is firing continuously, pushing the floor upward into your feet. When you release the ball, it does not fall because something pulls it down. It simply floats in space while the floor rushes up to meet it. From inside the box, the two situations are indistinguishable. No experiment you perform inside that sealed room can tell you whether you are standing in a gravitational field or being accelerated through empty space. Every measurement gives the same result. This is not a trick of perception. It is a precise physical statement. If gravity were a conventional force like electricity, you could detect it locally. In an electric field, a charged particle drifts in a measurable way. You can shield electric forces with conductive materials. You can distinguish between being pushed and being pulled. But gravity refuses to cooperate. Inside the sealed box, gravity and acceleration behave as identical twins. You cannot design an experiment confined within the box that separates them. Einstein realized that this was not a coincidence, but a profound principle. He called it the equivalence principle, and he described it as the happiest thought of his life. Because if acceleration and gravity are locally indistinguishable, then perhaps gravity is not a force in the usual sense at all. Consider what this means carefully. If a real force acts on you, it should leave traces. If I push you sideways while you are standing still, you feel that push. If an electric field accelerates a particle, your instruments record the drift. Forces reveal themselves through measurable effects. Yet in the sealed box, no such distinguishing effect appears. The acceleration of the rocket produces exactly the same phenomena as standing in Earth's gravity. The force you attribute to gravity could just as well be the effect of acceleration. That symmetry is too exact to ignore. It suggests that what we call gravitational force may simply be the experience of being in an accelerated frame of reference. Push the thought experiment further. Now imagine the box is not resting on Earth or accelerating upward, but falling freely toward the ground. The box and everything inside it are dropped from a great height. What do you feel? Nothing. You and the ball you were holding float weightless beside each other. If you had a scale, it would read 0. Inside the falling box, gravity has vanished completely. This is not speculation. Astronauts orbiting Earth experience precisely this condition. They are still deep within Earth's gravitational influence, yet they float because they are in continuous free fall around the planet. Gravity has not been turned off. It has become undetectable locally because everything shares the same motion. This is the key insight. In a sufficiently small region of space and time, free fall is indistinguishable from the complete absence of gravity. The only residual effects that remain are tiny tidal differences that appear when you compare separated points over larger distances. But locally, gravity can be transformed away simply by falling. That property is unlike any other force in nature. You cannot eliminate an electric field by choosing the right state of motion. You cannot make magnetism disappear by jumping off a building. Gravity alone allows this transformation. The equivalence principle, therefore, points toward a radical reinterpretation. Perhaps the falling object is not being pulled by a force at all. Perhaps it is simply following its natural path while the person standing on the ground is the one being accelerated away from that path. The sealed box reveals that gravity and acceleration are not separate phenomena. They are two perspectives on the same underlying structure of reality. Now take that sealed box and let it fall. Do not imagine a gentle drop. Imagine the box released from a great height, accelerating freely toward the earth. Inside the box, you release the ball from your hand and something astonishing happens. It does not fall to the floor. It floats beside you. Your feet are no longer pressed against the surface. Your stomach does not feel pulled downward. If you had a scale beneath you, it would read 0. Inside the falling box, gravity has vanished. Not weakened, not reduced, but undetectable. Every object shares the same motion. You and the ball, the air, every atom in the box are falling together. Because you all accelerate at the same rate, there is no relative acceleration between you. And without relative acceleration, there is no measurable force. This is not a philosophical statement. It is an experimental fact. Astronauts aboard the International Space Station experience exactly this condition. Many people say they float because there is no gravity in space. That is incorrect. At the altitude of the station, Earth's gravitational pull is still about 90% as strong as it is on the surface. Gravity is very much present. The station and everything inside it are simply falling continuously around the Earth. They are in orbit, which is just a sustained sideways fall, because the station, the astronauts, and every loose object inside share the same acceleration. Gravity becomes invisible locally. It leaves no trace in their immediate measurements. They drift in apparent weightlessness, not because gravity disappeared, but because nothing resists it. You have felt a hint of this yourself on a roller coaster. As the car crests a hill and plunges downward, there is a brief moment when your body lifts from the seat. Your stomach rises. Your weight seems to dissolve. For that instant, you are in near free fall. The seat no longer presses firmly against you because you and the seat are accelerating together. Aircraft used for zero-gravity training follow parabolic trajectories for about 25 seconds at a time. During that arc, passengers float freely inside the cabin. The engines are still running. Earth's gravity is still acting. Yet inside the aircraft, gravity is operationally absent because everything shares the same path. If gravity were a conventional force, this would be impossible. An electric field acting on charged particles cannot be eliminated by choosing the right motion. If a magnetic field permeates a region, it will reveal itself through forces on moving charges regardless of your frame of reference. But gravity alone allows this disappearance. When you fall freely, you do not feel pulled. You feel nothing. The only thing you ever feel is resistance to falling. The only time gravity becomes perceptible is when something blocks your natural motion. When the ground stops your descent, it pushes back against you. That push is what you interpret as weight. There is a subtle detail worth addressing. In a large enough falling box, tiny differences would emerge. Objects closer to Earth would accelerate slightly more than objects farther away. Two balls separated horizontally would drift slowly toward each other because they are both converging toward the planet's center. These are tidal effects. They reveal that gravity has structure across space. But these effects depend on the size of the region examined. Shrink the box, shorten the time interval. The tidal differences diminish without limit. In a sufficiently small patch of space and time, free fall is indistinguishable from the complete absence of gravity. This is the turning point. The falling object is not under a force in the usual sense. It is following its natural course. The person standing on the surface is the one experiencing force because the ground prevents that natural motion. Gravity disappears in free fall because free fall is not being acted upon. It is the default state. What you have called gravitational pull is actually the consequence of resisting that default. And that realization prepares the ground for an even deeper shift in how we understand motion itself. Everything now hinges on a reversal that feels almost impossible to accept. The only reason you feel gravity at this moment is that the ground is in your way. The sensation you call weight is not a pull from below. It is a push from beneath your feet, the atoms in the floor, bound together by electromagnetic forces. Resist being compressed. When your body tries to follow its natural motion, the ground prevents it. That resistance produces an upward acceleration. That upward acceleration is what you interpret as weight. If the floor were removed, you would not feel a downward force. You would feel nothing at all. Free fall is the state of zero force. Standing still on the surface is the state of acceleration. This is the conceptual inversion. In Newton's picture, you are at rest and gravity pulls you downward. In the deeper picture, the falling apple is the one at rest in a fundamental sense. It is following the straightest possible path available to it. The person standing on the earth is the one being forced away from that path. The chair beneath you is pushing upward. The electromagnetic interactions between your body and the surface are continuously accelerating you. You do not notice this acceleration because it is constant, but it is there every second. Remove the surface and the acceleration disappears instantly. That alone tells you which situation involves force. To understand what the natural path means, we must abandon the idea that straight lines are defined only in space. In everyday geometry, the shortest path between 2 points on a flat surface is a straight line. On a curved surface, that intuition fails. Imagine two travelers starting at the equator of the Earth, both walking due north along what feels like perfectly straight paths. They never turn left or right. Yet as they proceed, they draw closer together until they eventually meet at the North Pole. No force pulled them together. They simply followed the straightest paths available on a curved surface. Their convergence is a property of geometry, not a tug. Now extend that idea beyond the surface of a sphere to the fabric of the universe itself. Space and time are not separate stages. They form a unified structure called space-time. Massive objects like Earth alter that structure. They curve it. When an object moves through space-time, it follows the straightest possible path within that curved geometry. Physicists call this path a geodesic. In flat space-time, a geodesic appears as uniform motion. In curved space-time, that same straight path can look curved when projected into space alone. What you perceive as a falling trajectory is actually a straight line traced through a warped geometry. The apple dropping from a tree is not being dragged downward by a force. It is following a geodesic in curved space-time. Its motion is as natural as a stone rolling along a shaped track. Meanwhile, you sitting in your chair are prevented from following your geodesic. The ground exerts electromagnetic forces that continually redirect you. That redirection is acceleration. Acceleration is what forces feel like. The direction you call down is simply the direction in which the surface must push to keep you from following your natural course. This interpretation resolves the earlier cracks There is no mysterious action at a distance because nothing is reaching across space to pull. There is only local geometry shaping motion. There is no unexplained coincidence between gravitational and inertial mass because gravity is not a conventional force at all. Free fall and inertial motion become the same thing. The equivalence principle becomes obvious. An accelerating rocket and a person standing on Earth both experience force because in both cases something is pushing them away from geodesic motion. The shift is subtle but profound. Falling is freedom. Standing still is constraint. The weight you have felt your entire life is evidence not of a downward pull but of an upward push. You are not being dragged toward the center of the earth. You are being held away from the path you would otherwise take. And that path is determined not by a force field but by the shape of space-time itself. Once you accept that falling is the natural state and that weight is the result of being pushed away from that state, the remaining step is to understand what shapes the path itself. The answer is curvature. Mass and energy do not reach out and pull. They alter the geometry of space-time. Think again of the Earth's surface. A straight line drawn on a globe is not what it appears to be on a flat map. Airplanes flying from New York to London follow what looks like a curved arc on a map. Yet they are traveling along the straightest possible route on the curved surface of the planet. The curve you see is not the result of a sideways force. It is the consequence of geometry. In the same way, objects near Earth trace curved paths through space because space-time itself is curved. In this framework, gravity is no longer a force field but a statement about shape. Space-time tells matter how to move. Matter tells space-time how to curve. That compact description captures the heart of general relativity. When a massive body like the Sun exists, it modifies the geometry around it. Planets moving nearby follow geodesics within that curved geometry. Their orbits a constant inward tug, but the natural straightest paths allowed by the warped structure. If the Sun were suddenly removed, the curvature would change. And that change would propagate outward at the speed of light. There is no instantaneous influence. The geometry updates locally, and motion responds accordingly. This picture is elegant, but elegance alone is not enough. It must confront observation. The first major test involved the orbit of Mercury. Astronomers had long known that Mercury's elliptical path slowly rotates around the Sun. Most of that precession could be explained by the gravitational influence of other planets using Newton's law. Yet a small discrepancy of 43 arc-seconds per century remained. It was tiny, almost imperceptible, but persistent. Einstein calculated the curvature of space-time near the Sun using his field equations and found that the additional precession emerged naturally from the geometry. No extra planet was needed. No adjustment was inserted. The number matched exactly. That was the first confirmation that the curved picture described something real. The second test concerned light itself. If space-time is curved, then light, which also follows geodesics, must bend when it passes near a massive object. During a solar eclipse in 1919, astronomers measured the apparent positions of stars whose light skimmed the edge of the Sun. Their positions shifted precisely as predicted by general relativity, twice the amount expected from a simple Newtonian treatment. The bending of light was not metaphorical. It was measurable. Space itself was guiding the trajectory of photons. The third confirmation involved time. In a curved space-time, clocks do not tick uniformly everywhere. Near a massive body, time runs slightly slower than it does farther away. This is not a mechanical flaw in the clock. It is a difference in the rate at which time itself flows. Experiments have confirmed this effect with extraordinary precision. Clocks placed at different heights in a gravitational field accumulate measurable differences. Modern satellite navigation systems must account for this time dilation, or their positional accuracy would degrade rapidly. The curvature of space-time affects both space and time, and the effect is practical, not abstract. These observations do more than support a theory. They demonstrate that gravity behaves exactly as geometry predicts. Orbits shift because paths are curved. Light bends because space-time is shaped. Time slows because the temporal dimension participates in that curvature. Newton's law remains useful for everyday calculations, just as a flat map is useful for navigation over short distances. But when precision or extreme conditions are involved, the flat approximation fails. Only the curved description captures the full structure. Gravity is not an invisible hand pulling objects downward. It is the architecture of space-time guiding motion along its contours. There's one more layer beneath everything we have said, and it is the layer that unsettles the intuition most deeply. When we speak about curved space-time, it is easy to imagine space bending like a rubber sheet. That image is useful but incomplete. In the weak gravitational field near Earth, most of what causes objects to fall is not the curvature of space alone, but the curvature of time. Time itself flows at different rates depending on height in a gravitational field. Clocks closer to Earth tick slightly slower than clocks farther away. The difference is incredibly small, yet it is measurable and real. And that difference is enough to bend the natural paths that objects follow. Every object is always moving through time. Even when you stand still in space, you cannot stop moving forward through time at 1 second per second. Now imagine that the rate at which time passes is not uniform. Near the surface of the Earth, time runs a bit slower than it does higher up. An object following the straightest possible path through space-time will respond to that gradient. It will drift toward the region where time flows more slowly, not because something pulls it downward, but because the straight path in a geometry where time is uneven appears curved when projected into space. Picture two hikers walking side by side across a field, both aiming straight ahead. The ground under the hiker on the left is muddy and slows each step, while the ground under the hiker on the right is firm and allows faster progress. Even though both aim forward, the pair gradually veers toward the slower side. No sideways force is required. The asymmetry in forward progress alone causes the path to curve. Replace the hikers with the top and bottom of a falling object. Replace muddy ground with slower flowing time. The bottom of the object, slightly closer to Earth, experiences a slightly slower passage of time than the top. As the object advances through time, that tiny difference in rate bends its trajectory toward the region where time flows more slowly. The motion we call falling is largely a consequence of temporal curvature. This perspective transforms gravity from a pulling interaction into a property of the universe's structure. Objects are not yanked downward. They follow the straightest possible world lines through a landscape where both space and time are shaped by mass and energy. Remove the curvature and nothing would fall. Equalize the flow of time at all heights and the apple would remain suspended. The drama of weight and descent emerges from geometry, and yet this explanation, as powerful as it is, does not close the book. It shifts the mystery deeper. We can write Einstein's field equations and calculate how mass and energy determine curvature with astonishing precision. We can predict the motion of planets, the bending of light, the ticking of clocks, even the ripples of gravitational waves produced by colliding black holes. We can measure those waves as they stretch and compress space-time itself, confirming that gravity is not a force acting within space, but a dynamic property of space and time. But why should mass curve space-time at all? Why should the presence of energy alter geometry? The equations describe the relationship flawlessly. yet they do not reveal the underlying mechanism. In this sense, physics has not eliminated mystery. It has refined it. Newton left us puzzled about how a force could act across empty space. Einstein removed that puzzle and replaced it with a deeper one about why geometry responds to matter. Progress does not end questions. It relocates them to more fundamental levels. The familiar sensation of weight becomes evidence of curvature. The falling apple becomes a lesson in the structure of reality, and beneath that structure remains an open question, inviting the next leap of understanding. Gravity is not pulling you down. It is the shape of space-time guiding you along the only straight path available. What remains is to understand why that shape exists at all.